This video is on how things dissolve. So first we want to talk about solutions. Solutions are a mixture. It is a homogeneous mixture of two things, so they're not actually chemically reacting, but the particles are suspended. They do not settle out, and they're really, really tiny particles, so tiny that you can't use a filter to separate the two components of the mixture, and the particles are really tiny, so they don't scatter light at all. There are always two components to every single solution, and those two components are a solvent. This is the substance doing the dissolving, and the solute. That is the substance being dissolved. And those two terms are very different, but sound very, or at least start with the same three letters. So you need to make sure that you have it in your head. Solutes are what's being dissolved, and solvents are what are doing the dissolving. So solvents dissolve solutes. If I had a solution of sugar water, it would look just like water until I went to take a sip, and then I would know that it was sugar water. And in that case, sugar is my solute and water is my solvent. Water was doing the dissolving. And really in this video, we're going to talk about how water does its dissolving. Water is a very popular solvent and is often referred to as a universal solvent. Doesn't mean it can dissolve everything, but it can dissolve a lot of things. And we'll look at the reason why water can dissolve a lot of things. Now, solutes, so those are the things being dissolved, can be electrolytes or non-electrolytes. Now, we heard this before when we were talking about bonding. Electrolytes are things that can conduct an electrical current when in solution. And so the example we had when we went through bonding was with salt water. Salt actually splits up into ions. And because there are those charged pieces floating around in water, it can complete the electrical circuit. So when we talk about electrolytes, we're talking about things that have ions, things that are made of ions. So like salt being dissolved in something else. Solutes can also be non-electrolytes. So these are things that aren't made of ions, like any of your molecules. Sugar water sugar is not an electrolyte. It's not made of ions. It's all non-metals. And so when you dissolve sugar in water, it does not split up into ions. So there are no charged pieces. You just have sugar molecules that are being separated from one another, and they're floating around neutral. So sugar water does not conduct electricity. Solutes of ionic compounds and certainly highly polar molecules are electrolytes. And water is a solvent. It's going to be a non-electrolyte. And only solutions of electrolytes conduct electricity. All right, so the solution process. It's going to start with what you know about water. And you do need to know about the structure of water. You need to know that water is polar. You need to know that water has charged ends, and you need to be very familiar with what charges each end of water happens to have. So if I have a water molecule, I've got my oxygen here, which is red with its two little unshared pairs, and then my two hydrogens that are bonded to it. Oxygen's way more electronegative than hydrogen, and so the electrons spend more time with oxygen than they do with hydrogen. So oxygen develops that slight negative charge, and each hydrogen develops that slight positive charge. All right, so you need to make sure that you know with water that oxygen is slightly negative and hydrogen ends are slightly positive. And they do have that bent shape because we've got two unshared pairs on oxygen. Now, because we have hydrogen directly bonded to FO or N, and in this case O, we have hydrogen bonding going on between water molecules. And so this is going to kind of come into play when we talk about the energy that's involved when we make solutions. Because water's all attracted to water, and when we mix it with something else, we kind of have to break these attractions so that it's attracted to the other substance to do the dissolving. All right, so water molecules are going to surround ions or other polar molecules one at a time, forming these hydration shells. So basically, water is going to surround them and keep the ions separate from one another. And that is what's happening when something is dissolved. So let me show you my example of salt water. So I've got water that's all hydrogen bonded to other water molecules. And then I have salt, which is ionically bonded. The sodium is ionically bonded to the chloride ions. And so they're all attracted in that crystal lattice structure. When I mix salt with water, what happens is that the water molecule with its slightly charged ends, the oxygen being slightly negative and the hydrogens being slightly positive, the ends of water end up becoming attracted to these full charges on our ions. And so the hydrogens, with their slightly positive, are going to be attracted to this big old negative here on this chloride ion. And the oxygen is, with its slightly negative charge, is going to be attracted to this sodium ion, and then it's going to surround them and separate these two from one another, making it go into solution and dissolve. So here's what that's going to look like. Here we have our sodium, and you'll notice how the water molecules are oriented around this sodium. The oxygens, which again are red, are all pointing towards this positive ion because the oxygen end of water is slightly negative. And this is a hydration shell, so it's surrounded by water. Now, other water molecules are going to be attracted to this chloride ion. And again, notice the way the water molecules are oriented. The slightly positive end of water is attracted to this this full on negative of this chloride ion. And again, the water molecules surround the chloride ions. And when I keep these ions separate from one another, we're not going to see a solid. We're going to have salt water. So the ions are floating around in solution. Here's another look at the same sort of thing. I've got my sodium chloride here, and I have my water molecules. You can kind of see your hydrogens with their slightly positive charge and our oxygens with its slight negative. So the water molecules are going to be attracted. Here I've got an oxygen, which is slightly negative, attracted to this positive piece here on the solid. And it ends up being surrounded. It will be attracted and then surrounded by other water molecules. Notice all the oxygens are pointing towards that positive ion because all the oxygens on water are slightly negative. Here I have a water molecule with its slightly positive end with the hydrogens there attracted to this negative ion. And so again, what happens is other water molecules will join in and be attracted to that negative ion, and the water molecules will be oriented this way to where all their hydrogens, which is the slightly positive end of a water molecule, are pointing in towards that. And so again, these are hydration shells or solvation. Here's a nice little video. We'll look at this with an animation. And with this one, we've got salt. We've got our sodium ions and that are white, and our chloride ions, which are green. So when we put salt in water, we're going to add some salt here, and then we'll probably stir this around. That allows the water molecules to come in contact. Notice all those slightly positive hydrogens are attracted to that negative chloride ion. And then now we see the white sodium ion being surrounded by some water molecules with the oxygen ends being pointed in. And this is how the dissolving process happens. And once that happens, other water molecules can come in to dissolve more and more. And again, this would be dissociated where the sodium and the chloride ions were together, and now they are apart, so they dissociate from one another. Oops. All right. Now, this is going to be an example of what I was talking about with electrolytes versus non-electrolytes. Electrolytes would be here sodium chloride. Sodium is red and chlorine is blue, and it would be a solid. And when they dissolve, it's going to separate into the separate ions. All right, so this would be an electrolyte solution made up of ions. When I have something like sugar, it's a molecule. It's all nonmetals and has those covalent bonds. So it's not made of ions. So when we put sugar in water, notice it does not separate into individual pieces or ions. All we do is separate the molecules from one another. Now, 3 factors that affect the rate at which a solid solute dissolves in a liquid solvent. So we're trying to dissolve something in a solvent. So let's just say we're dissolving something in water, since water is a very popular solvent. I say that if you know how to make sweet tea, you already know these 3 factors. So when you make sweet tea, we're going to use sugar crystals and not sugar cubes, because increasing the surface area is going to increase those factors. Sugar cubes, what happens there is that the solid pieces that are trapped inside the cube the water can't get to those until the outer pieces are dissolved. And so it takes a lot longer than if you were to have sugar crystals. Then water can get all around each of those molecules and dissolve things a whole lot faster. So the more finely divided the substance, the greater the surface area. So the more surface water molecules can access, and the quicker the substance is going to dissolve. So we increase surface area by smashing it into bits. If we can grind things up, our reactions and our dissolving is going to happen a whole lot faster. Here's a visual for that. So you can see these red water molecules can only get to the ones on the surface. They can't get to the particles that are trapped on the inside until the outer ones are dissolved. So if I smash the solid into tiny little pieces, now the water molecules can access more of the solid and dissolve it. The next one is stirring. So when you're making sweet tea, you add sugar to the tea and then you stir. Another term for stirring is agitating, but you can use stirring, it's fine. So more stirring, the more particle movement. So you get the water molecules around those pieces of solid. And so it is going to dissolve quicker. The next one would be if you're making sweet tea, you always add the sugar to the warm tea. You don't wait for the tea to cool down before you add your sugar. So heating the solvent is going to help. And that has to deal with the kinetic molecular theory. So the more heat you have, the more particle movement you have. So you've got your own little like molecular mixer going on in there. You also have more energy so that you can break some intermolecular forces between the solvent particles, and you're also going to have greater solubility, which we'll look at a little bit later. All right, so knowing these 3 factors can really help you not only with dissolving, but also reaction rates, and we'll talk about those a little bit later. So how do we know if something will dissolve in something else without actually trying it? Well, we have a little saying in chemistry, and this is not one that I made up, but it lets you know what will dissolve and what. So the phrase is like dissolves like. That means polar solvents will dissolve polar solutes. And that's because you get this slight attraction. You got a partial positive attracted to a partial negative, and so they can separate the particles from one another. Non-polar solvents dissolve polar solutes. So you may have run into this if you like to do any sort of painting and you use oil-based paints. Oil-based paints at the end, when you're ready to clean up, if you have forgotten that you're using an oil-based paint and you take your paintbrush to the sink and start to use water to clean up, it just makes a giant mess. It looks like it's getting worse and not cleaner. So that's because water is polar and your oil-based paints, oils are non-polar. And so they're not going to dissolve one another. So what you can do is with your paintbrush using oil-based paints to clean up, you're going to use paint thinner or turpentine or gasoline. You're going to use something else that is nonpolar, and then then you can clean the paint off the brush, and then you can use water to kind of wash your hands and things like that once you've gotten the nonpolar solutes off. Another example of this would be trying to remove the adhesive, like off of a sticker when you buy something and you want to remove the price tag. Sometimes that can be really, really difficult. Adhesive tends to be nonpolar, so you can use, now if it's safe on whatever product we're talking about, WD-40 is a fantastic nonpolar solvent, and it will dissolve the adhesive, and then you can just kind of scrape it off, and it actually works really, really well. All right, so like dissolves like, polar dissolves polar, and nonpolar dissolves nonpolar. Well, what about ionic? Now, generally, we don't have ionic solvents. So if we think about water, water can dissolve ionic compounds because the one thing that they have in common are charges. So it's really more like charged dissolves charged. Water has charged ends, and it's attracted to those charged ions and forms those hydration shells. Not all ionic compounds are soluble in water, and we'll look at in a later lesson on how do we know which ones are, but a lot of them really are soluble in water because water's polar. So the charged ends attract the ions in the ionic compound and keeps them away from one another, making them go into solution. Ionic compounds are not generally soluble in nonpolar solvents because there's nothing to attract. The ions are positive and negative and are attracted to each other. Nonpolar solvents have no charges, so there is nothing to pull those ions away from one another.